process, manufacturing process simulations, modeling and optimization of manufacturing process, and CAR and CAM. And also received sponsored research projects from the Department of Science and Technology, DST, and the Aeronautics Research Development Board. I would like to invite Dr. Suresh on the stage.
Good afternoon to all. Thank you for your kind introduction. This is not working. Otherwise, you keep the keyboard. Okay. Are you able to hear me? First of all, I would like to thank the management of GRIET and the advisory committee of ICMPC for inviting me to deliver the keynote speech in this prestigious ICMPC conference. I was associated with this conference from first edition, and it was started with very humble beginning by Professor Swadesh Kumar Singh sir, and now it is one of the very reputed conference in India, as well as many people are participating from the abroad, and it is a great honor to deliver a keynote in such a reputed international conference. So without much delay, let me start my presentation. My today's presentation is on image processing based approaches for strain measurement in sheet metal forming operations. Before to talk about this topic, let me give a brief overview how we started this work. Strain measurement is one of the important thing in a sheet metal forming. First, we can use the different devices for measuring the strains that I am going to discuss in the coming slides. There is some automatic portable strain measurement systems, but unfortunately those systems are not available in India. We use it to import from foreign countries. When I approached some of the companies, they quoted around 15 lakh. Then we thought of why can't we develop indigenously, because now Indian government is also giving much importance to make in India. Our Honorable Prime Minister Modi ji also continuously stressing make in India, indigenization. That is most important if we want to become a developed country. It is very important to make the products indigenously. Of course, when I am discussing with some of the DRDO scientists, they are also expressing even simple components also we use it to import. For example, honeycomb structures. We all know honeycomb structures. But you know, even though we are having a population of 100 crores, there is no manufacturing industry which will manufacture honeycomb structures. We use it to import. Similarly, carbon fibers, we use it to import. So it is not only research is not only doing some basic research or advanced topics. Our research should also focus developing the products indigenously. With that motivation, we wrote a proposal to DST Device Development Program. There is one program, DST Device Development Program. To that we wrote a proposal of 18 lakh to develop a portable device and software for measuring the strains in sheet metal forming applications. And whatever we have done as a part of that project, I am going to present in today's presentation. Now, the content for today's presentation is I will give you a brief introduction how the strain is measured in sheet metal forming applications. After that, whatever hardware that we develop for capturing the images that we are going to discuss. After that, there are two methods we use for strain measurement, circle grid analysis and square grid analysis. Whatever software that we develop, I will briefly show you that software. Then how we validated by different experiments we are going to discuss. After that, we did some basic studies on developing 2D DIC systems using open source softwares. Those things also I will show you few things. And what are our future plans on strain measurement through image processing and developing some strain measurement systems indigenously. Those things I will briefly discuss. And I will also show you some of the published articles on the work that we have done on strain measurement. Now coming to the strain measurement in sheet metal forming, if you want to measure the strain, the general method people follow is they will print a grid of small circles or squares on a flat sheet. For example, here I have shown different types of grids. You can see the circular grid, square grid, butted circles, filled circles. Like this, either circular grid or square grid will be printed on a sheet, and then the sheet will be deformed. Now the question comes how to print these grids. Generally people use either electrochemical etching, screen printing or laser engraving. These are the three methods generally people use it to print the grids. Once you print the grid, then the sheet will be deformed into required shape. Whatever shape you want, you have to deform. As you know, once it is deformed, the circle is going to become an ellipse. The regions where there is a more strain, there the elongation will be more. Similarly, the major axis length and minor axis length of the ellipse also will be more. By measuring the major axis length and minor axis length at different locations of the deformed component, we are going to evaluate the strain at that particular location. This is how the strain is measured. So if this is the ellipse with a major axis length D1 and minor axis length D2, then the major strain can be calculated as ln of D1 by D, and the minor strain will be calculated as ln of D2 by D, where D is the original diameter of the circle. Original diameter of the circle will be generally 3 mm to 5 mm. Okay? And D is the original diameter, D1, D2 are the major axis length and minor axis length of the ellipse. Now the question comes how to measure this major axis length and minor axis length. This is the place where these portable devices or strain measurement systems will come into picture. Okay? So this is how the grid will look. Once you print by screen printing, the first metal sheet if you see, those are the grids printed by screen printing. The second one is electrochemical etching and third one is laser engraving. Now this is the sheet and we deformed that sheet into hemispherical dome. You can see the dimensions of the ellipses at different locations. If you see at the pole, that means at the top end, the circle remains as a circle, it is not deformed much. That means there the strain is very less. If you see at the corners, the circle become an ellipse, and the major axis length, the minor axis length, you can see based on that you can understand the extent of deformation in the formed component. Okay? So this is how the grids will look when you print. Now in order to measure this strain, there are two methods. You can measure by using manual methods or you can use automatic methods. Again, in automatic methods, we have single point strain analysis and multi-point strain analysis. Single point strain analysis means we are going to measure each grid one by one. In multi-point strain analysis, the images of all the grids will be captured at a time and it will give the distribution of strain over the formed component. Okay, whatever system that we develop in whatever system that I am going to discuss in today's talk, that is mainly focusing on single point strain analysis system. That means we are going to capture the image of each ellipse and we are going to measure its major axis length, minor axis length, and we are going to evaluate the strains. Now, how do we measure this major axis length and minor axis length? As I told in the previous slide, there are manual methods and automatic methods. In manual methods, people generally use mylar tape. This is very old technique. Nowadays, no one is using. And another is a traveling microscope. This formed component will be kept under this traveling microscope, and there will be a crosshair marks. We will align the crosshair marks at the extreme ends of the major axis, and then we will see the reading. Similarly, you will align the crosshair marks along the minor axis, and then you will see. All of you know the microscope. So people use traveling microscope, or another is stereo microscope. Under stereo microscope, this formed component is placed. Here again, when you placing the component, also it is a challenge. You have to orient it properly. For that they put some clay, and then they will try to orient under the eyepiece of the microscope. And it will have an image analysis software. It will display the image. Then people will pick two endpoints of major axis length. Then it will give the major axis length. But how do you know exactly these are the two endpoints of major axis? That depends upon randomly he may click. So the accuracy is questionable. And here one more problem is, okay, if it is a small component, I can carry it and I can keep it under microscope. If the size of the component is very big, I cannot carry that component here. At the same time, I cannot take this microscope to the shop floor and in order to measure the strains. This is the place where the requirement for portable strain measurement system will come into picture. Okay, there are some commercial automatic strain measurement systems. If you look at this picture, the first one is FMTI, commercially available single point strain analysis system. And another is GPA, grid pattern analyzer. You can see how they are keeping on the formed component. The image will be displayed on the computer screen, and it will have an associated software in order to measure the strains. Similarly, in 2D DIC systems, people use camera. They will apply the speckle pattern. I will show you in the coming slides. And those images will be analyzed for measuring the strains. This is a 2D, 3D DIC systems. People use this kind of systems. Now, what we have done as a part of our research work, for automatic strain measurement system, we can classify into two broad categories: full field strain analysis and single point strain analysis. Again, in full field strain analysis, there are two categories. One is 2D DIC, that means two-dimensional digital image correlation. We are going to capture the multiple images, we are going to correlate in order to evaluate the strains. Okay. And similarly 3D DIC, if it is a three-dimensional shape, how to measure the strains automatically. For that we use 3D DIC systems. And in single point strain analysis, just now we have seen where we are applying the grid and we are trying to evaluate the strains. In this, we are going to use either circular grid or square grid. For circle grid analysis, again we proposed three different algorithms. One is arc support line segment algorithm, which is people developed this algorithm for detecting some of the defects in PCBs, elliptical defects. So we try to use that algorithm for measuring the ellipse dimensions to evaluate the strains. After that, another segmentation method, and a third one is a least square fitting. We set this two as automatic because once you capture the image, it automatically identifies the edges and it fits the ellipse. That is why we call it as automatic. In least square fitting, we call it as fail-safe or semi-automatic. For example, in your image, the noise is more. Then the software may not detect the edges automatically. Then here what we provided is you can pick 5 points over the edge of the ellipse. Automatically it will fit a least square ellipse passing through those 5 points, and the software will evaluate the major axis length and minor axis length. So these are the three algorithms that we propose for circle grid analysis. And for square grid analysis also we propose two algorithms. One is Hug transform with clustering, and another is a projective collimation method. Okay, now let us go to the next slide. So this is the software part. Before that, we need to capture the image. To capture the image, we need some device, we need some hardware. So we made so many trials, different, we try to use our cell phone, we try to use some cameras. Finally, what we thought is, we took this USB microscope. We have taken the USB microscope and we modified this USB microscope. We made necessary changes in the USB microscope to capture the deformed grids. Okay, what we did, all of you might have seen USB microscope. One reason for taking this USB microscope is it has inbuilt LED. So whenever I am capturing the image, I need not provide external light. It illuminates the surface and I will get a good images. This is one reason for taking this USB microscope. And the cost of USB microscope is also very less. If you see in online, the cost is also very less. What we have done here is, this USB microscope, the front end, there will be an end cap. We removed that end cap and we designed our own end caps. We did some trials and we designed these end caps with different opening diameters. If you see the end caps, opening diameter is 5 mm, 10 mm, 20 mm. For different opening diameters, the height of the end cap is also different. Why we have chosen different end cap diameters? For example, if you take a sheet metal component, it may have different curvatures. In order to accommodate different curvatures, we developed our end caps with different opening diameters. Okay. So depending upon the opening diameter, the height of the end cap also will change. These are the 3 end caps that we have developed in order to measure the strains over the formed components with the different curvatures. And these end caps we can print it by using 3D printers. These are all 3D printed parts. Then we captured the images using this particular hardware. These are the images, captured images. Then we converted into binary images. And you can see these images, after converting into binary images, still there is a noise. My goal is to identify the edges of an ellipse, but there is some noise which may create a difficulty in automatic detection of the edges of that ellipse. So what we have done is, instead of using the end cap directly, we provided a side lighting. We removed the existing LEDs from the microscope and we modified the end cap with side light. You can see in the figure 2, the end cap with side light, and we made necessary connections, because this LED, once you put a new LED, it requires a power. So we connected from wherever the existing LED is getting the power to the same thing we connected, or we took the power for this side LED. Once you use the side LED, then there is a reduction in the noise. You can see the second set of images. There is a reduction in the noise. Once the noise is less, then it is easy for us to identify the edges of that ellipse. Okay, this is the one modification that we have done in the end caps. You can use the plain end caps or end caps with the side lights in order to capture the images. And in order to accommodate, or in order to capture the images from the formed components with the different curvatures, we printed end caps also with the different opening diameters. Okay, this is the overall picture of hardware development, and we got an invitation from Hardware X journal, which is a very nice journal, which will publish mainly the hardware aspects. We got a special invitation from editor to submit our work. So we submitted and we published in this journal. We have shared all the STL files. So if you want to make the same hardware, you can also make. So we want to make it available to all. So we shared the complete details to that journal. And also, not only we developed 2 different types of hardwares. We used the generic microscope, which is shown in the image A. And we also used another microscope, which is called a GSAS. This is, people are using this for some inspection applications of electronic components. This is also one kind of inspection. So we have used this GSAS microscope, and we developed different end caps for this microscope also. Whatever picture C there, that is the commercial device. These are what we have developed as a part of our project for capturing the grids. Now, okay, the images are captured. The second step is we need to measure it. So starting with circular grid analysis, as I have shown in my earlier slides, we proposed 3 different algorithms. First one is arc support line segment method, and the second one is least square fitting. I'm not going to details of this algorithm. You can refer our paper, which is published in Journal of Strain Analysis. These 2 algorithms and all the results we published in Journal of Strain Analysis, and the details are given at the end of this presentation. So this is how the GUI will look. This is the software. We developed the code in MATLAB, and we provided a very user-friendly graphical user interface so that it will be easy to use the software. If you look at this software, before to measure, first you have to calibrate. So what we will do is here load button is there. You will keep the hardware over the circle of known dimension, because original circles you printed with let us say 3 mm. I capture the image of that circle and I will click on the load. Automatically the image will be displayed in that image window. After that I will click on the measure. Once I click on the measure, it automatically detects the edges and it will show the dimensions in terms of pixels, because image is always in terms of pixels. Then once it displays on the pixel, on the side you can see here it is in mm. It is displayed as 394 pixels. This is equivalent to 3 mm, because original image, whatever I uploaded for calibration, I know the original dimension. I will enter this as a 3 mm. Then the system is calibrated. Next, now you can capture the image of deformed grid. That means you can capture the image of ellipse and click on the load, it will display there. Then you just simply click measure. Automatically it will display the major diameter, minor diameter in mm. And it will evaluate the strains and it will display the strains in the strain window. If you want to plot it, it will plot it. Whenever you capture the image, if there are more than one ellipse in your image, then we provided here with ROI button, region of interest. So you can simply drag one and create one rectangle that will be cropped and it will capture the edges of that particular ellipse. So you can also select the region of interest. And you can also import, once the data is measured, you can import to Excel for further processing. This is how the graphical user interface will look. Here I put automatic and semi-automatic, because once I uploaded the ellipse, if the edge is not detected, here you can see the edge is detected and it is showing the major axis and minor axis, and its dimensions are displayed here. In case if this edge is not detected, then you select the semi-automatic radio button and you select any 5 points over this ellipse. It automatically fit an ellipse and it will measure the major axis length and minor axis length. This is the software that we developed for circular grid analysis using 2 different algorithms. Okay, and we also provided there is something called as forming limit diagram, which is used for evaluating the formability of the materials. People will construct this forming limit diagrams once the new material comes. In order to understand its formability, they do a Nakajima test and they will construct this forming limit diagram. And there are also some theoretical methods to develop this forming limit diagrams, theoretical models. Some of the theoretical models we implemented in this software so that people can use the theoretical forming limit diagrams in order to evaluate the strains. Once the strains are measured, they can superimpose over this forming limit diagram and they can check whether the formed component will be safe or not. The third algorithm we propose. Why we proposed this third algorithm? Whatever algorithm that is there earlier, that is arc support line segment algorithm, that algorithm is working very well with the laser engraved grids. Laser engraved grids are very sharp and it is detecting the edges very easily. But we faced some difficulty in automatic edge detection of screen printed grids and electrochemical etched grids. For this, again we started working. We captured the original image, then we converted into a grayscale image, denoising by using different filters, then segmentation, then edge detection. Edge detection, again here you can select the mean ellipse, inner ellipse, outer ellipse. Whichever ellipse you want to select, you can select that one. So we provided those options also. You can also estimate the thickness, because once you see with the naked eye, the thickness may appear very small, but that also will have an effect on the strain measurement. So we provided an options so that the user can select whichever ellipse you want. You want to measure the inner, outer or mean ellipse. Okay, and we developed the graphical user interface for this also in Python. You can see here, here you can select the material also. And we provided one advanced tab where you can change the kernel size, Canny thresholding. These options also we provided in this software. Here also it will, you have to do the calibration and then measurement. So this is the third algorithm that we propose. So these softwares, all these things we published in Software Impacts. In that paper you can see the details of this software. And this software, this third algorithm, it is under review. It is not yet published. And other algorithms, first two algorithms, and the strain measurement, Journal of Strain Analysis, you will get the details. Now coming to the square grid analysis. This is another method. Here people will print the square grid. Once the sheet is deformed, this square is going to become a quadrilateral. Within that quadrilateral, you have to fit an ellipse, maximum size ellipse. Then we will measure the major axis length and minor axis length to evaluate the strains at different locations. Okay, for this we proposed two algorithms. This is a projective collimation, and another is hug transform plus clustering. There are different steps. Like here you can see input image, then we converted into grayscale image, then Gaussian blurring, Otsu binarization. We applied some morphological transformations, then contour detection, hug transforms, clustering. Then it will detect the 4 lines. Then we have to identify the 4 corner points. Here the basic idea is once you capture the quadrilateral, the software should identify the 4 corner points. With those 4 corner points, we are going to fit a maximum size ellipse. For corner detection, we use Harris corner detection, but it didn't work. It is working on a plain paper without any noise because the sheet metal is having some noise. So we couldn't able to detect the corners automatically. Then we followed this procedure for automatic corner detection and then ellipse fitting. You can see in the last picture, the ellipse is fitted nicely within that quadrilateral. Here also you can see. Here also the same algorithm, again same graphical user interface, whatever is developed for circular grid analysis. Here we provided one more tab for square grid, and the same procedure you have to follow, automatic or semi-automatic. In semi-automatic, manually you will pick the 4 corner points, then it will fit an ellipse. Whereas in automatic, once you upload the image, the corners are detected automatically, the ellipse will be fitted, the strains will be displayed in the strain window, and if you want, you can plot it or you can import it. Okay, this is how the screen will look. We implemented this in the Python code also. Here you have to check the square box against the square grid. You can change the settings. Then you can see here this is the quadrilateral and this is the maximum size ellipse it is fitting, and it will display what is the strain at that particular location. This is about square grid analysis. Okay, it is not just enough, okay, I developed the software, we developed the hardware. It is not enough. You have to validate whatever system that you develop. So we have done a very detailed validation studies. For validation, what we have done is we took the flat sheets and we printed the ellipses of known dimensions in different orientations. Here you can see copper sheet, steel sheet, aluminum sheet, because different sheet metals may have different luster. So we should be in a position to identify the grids on any sheet metal. So we have taken 3 different sheets. We printed the ellipses in different orientation, both open as well as filled ellipses. These are the images, captured images. Then this is the steps that we follow for measuring. Then we measured what is the deviation between the major axis length and minor axis length. And also, when you print the circular grid, let us say I printed 3 mm grid. There may be some deviation during the printing also. So what we do generally, we will upload one image and we calibrate. When I upload the second image of same 3 mm diameter circle, I may not get exactly 3 mm because of variations in the printing method. So we tested that also. We captured around 20 or 30 circles, and we also identified what is the deviation in the printing method. You can see here it is around plus or minus 0.03 mm. Deviation is there in the printing method itself. And these are the variations in the major axis length and minor axis length. And detailed, we also compared, okay, we captured the grids with our device, we captured the same grids with the commercial device. Is there any variation between the two? The maximum variation that we found is around less than 2%, and we also did some statistical studies to check whether this is acceptable or not. And okay, you are capturing the grids from flat sheet. What is going to happen once it is formed? Once it is formed, the grid is going to deform. Whether your device is going to automatically detect the edges or not. For that, what we have done is, now we didn't take different sheet metals. Already earlier we validated it is able to capture from any metal sheet. Now we took only one material, that is aluminum we took. We printed the grids by using different methods, electrochemical etching, laser engraving, screen printing. And then we have applied different levels of deformation. The grid should be able to measure the smaller strains as well as larger strains. So we deformed to different levels. You can see here 45 degree. This is a dome shaped component we formed in incremental forming. I don't know how many of you know incremental forming. It is a die-less manufacturing process. Here we don't require any die, unlike deep drawing or stamping where we require die. We will hold the sheet on CNC milling machine. CNC milling machine, many of you may know, which is used for cutting. Instead of using for cutting, we will remove the cutting tool and we will put one blunt tool with hemispherical headed. Then we will generate the tool path. The tool path will guide the tool and it is going to deform the sheet in whatever shape you want. This is very interesting technique. Ford Motors extensively working to make it happen on their shop floor, and Ford, Boeing also funded a lot for this, for the development of this process. This is still in research phase, but many people are, mainly Ford and Boeing, they are extensively working on this incremental forming. So we formed these components through incremental forming and we induced different levels of strains in the formed component. After that, again we captured the images by using two different hardwares. We developed generic USB microscope and GSAS. Using both devices that we developed, we captured, and we also captured using a GPA, that is commercial device, and we studied is there any variation, and we did some statistical studies. Finally, what we found is you can use any hardware, that is the two types of hardware that we developed are commercial available hardware. All are giving statistically acceptable results. And also we have done this kind of studies. You can see the circular grid, square grid. What we have done here in the third case is circular square grid. Within the square we also inscribed the circle. Then we deform. Then this circle is going to become an ellipse. And this square grid algorithm we use, and we fitted the ellipse. That ellipse is matching with the deformed ellipse or not. That also we checked, and it is, you can see there also deformed ellipse and fitted ellipse are same. Because from the square grid, once it is deformed to quadrilateral, I am fitting an ellipse, maximum size ellipse. Is that ellipse is same as the ellipse that you will get by printing a circular grid or not? That also we have checked it. Okay. This is about a single point strain analysis system, both hardware and software, that we developed as part of our DST project. After that, we also took some interest to study the full field strain analysis. And in full field strain analysis, we started with the 2D DIC system. In 2D DIC system, instead of using commercial cameras, nowadays mobile cameras are coming with very high magnification. So we thought of using a smartphone camera to capture the images, and we analyzed those images using open source software called as NCAR. There are many open source softwares, so we selected NCAR for full field strain analysis. This is what is called a speckle pattern. What people will do is they will sprinkle white and black paint over the specimen. They will create a speckle pattern like this. So this speckle pattern is very important. How you will apply your speckle pattern, that will decide the results of strain measurement. There are some good practices for applying the speckle pattern, you can refer. Now after that, what we have done is we have done the tensile test. Once we are doing the tensile test, using mobile phone camera, we recorded the test. From that video, we generated the images. These images are given as an input to NCAR software, and this NCAR software will analyze these images and it will generate the strain in X direction and Y direction, 2D DIC. You can see this is the strain distribution in X direction and Y direction. Here you can see this is the component with a speckle pattern. You can see here the necking started, and if you zoom it, here just the crack is started, crack initiation was started. And in the strain distribution that we got from DIC, also it is showing this is the region where the strains are very high. You can see the red region and what is the strain at this location. So wherever the crack is initiated at the same location, it is able to show what is the strain at that location. Okay. And we extended this test by making different specimens. These are some of the specimens people use for fracture studies. This is a notched specimen, specimen with circular hole. This is a notched specimen. And then we apply the speckle pattern, and we captured the images, and we processed it with NCAR software. Whatever force displacement data that we got from the crosshead of UTM machine, we compared that with force displacement data that we calculated from DIC software, and you can see there is very good correlation between the two. You can see this is the crosshead displacement and DIC. It is having very good correlation. Now what is our future studies? We are planning to develop 3D DIC systems. These 3D DIC systems are very expensive, around 75 lakh to 1 crore if you want to buy this kind of systems. So we want to develop this kind of three-dimensional digital image correlation systems for strain measurement in sheet metal forming. So what is our idea here? You can see this is the formed component. Okay, over the formed component you can apply the grid, or you can apply the speckle pattern, and then you will deform. In this static measurement, the static measurement means post forming we will measure. We will apply the grid like circular grid or square grid, we will deform. That formed component will be kept on this rotary table, and this is the camera. When the rotary table is rotating, your camera will capture the multiple images. These images will be stitched together, and we apply our algorithms for automatic edge detection, and it automatically calculates the strains at different locations, and it will generate a contour plot. This is one project, and we are having different ideas how different types of grids. And this is another idea. This is for a dynamic strain measurement system. That means that during the forming, we are going to create one rig with multiple cameras. So when the sheet is deforming, these cameras will capture the images. And these images will be analyzed using some open source softwares. And we are going to get the strain distributions at different stages of the forming. Instead of post forming, during the forming itself, because we are capturing the images continuously during the forming. Let us say I am going to form a dome of 50 mm height. Okay, once it is deformed to 10 mm, I want to know what is the strain. So at 10 mm height, already I have an images. I process those images and I am going to get the strain distribution. 20 mm height, again I have images, so I will process those images and I will get the strain distribution. This is one idea we have. And these works are published in this Journal of Strain Analysis, where you will find our first arc support line segment algorithm and least square fitting algorithms. Those studies we published in Journal of Strain Analysis, and square grid analysis we published in measurement. All the validation results we published in process mechanical engineering. The studies related to hardware is published in Hardware X, and the software, entire software as a bundle, we published in Software Impacts recently. These are some of the important papers, and this work, it is not possible to complete this kind of work without funding. We got funding from DST, DDP, and we acknowledge the funding that we received from DST, DDP. And another most important thing is these studies are not possible. I have not done. Okay, I have not done. This kind of studies are not possible with a single person. The credit goes to our students who worked with us. Many students worked with me as a part of their projects. Mr. Pankaj, who is my PhD student, very sincere guy. Recently he submitted his thesis. And my another student, Mr. Tejas from Electronics Department, and Mr. Guru from Electrical Department. He is in 4th year now. He also got thesis. He did his thesis recently in Japan. 6 months Japan, he got an opportunity, fully funded thesis he has done, and he came back recently and is planning for MS. He has done excellent work. He published 2 papers with us, Mr. Guru and Mr. Sriram, another mechanical student who worked on the square grid. And along with me, some other faculty members also involved. Dr. Sudha from Electronics Department, who is expertise in image processing, and another faculty from our department, Professor Amrita Priyadarshini. We are all team members. We all worked together for 3 years to develop this kind of systems. This is a collective team effort. Because of that, we are able to do these things. And thank you for your patience. I took, I think, 1 hour. Okay. And if you want any technical details, you can refer those papers. I presented whatever work that we have done as a part of this project. Maybe it is interesting to the people who are working in sheet metal forming. I know how difficult it is to measure the strains by using stereo microscope or traveling microscope. This is a very user friendly. Just to keep the device on it, it will capture, it will measure, and it will display the strain. It is a single click. So it is a very user friendly system. Okay, this is the work we have done, and thank you very much for giving this opportunity to share our work in this 14th ICMPC conference. Thank you.
Any questions?
If you have any questions, you can ask. Actually, we didn't measure with stereo because our goal is to validate our system with commercial device, commercially available portable strain measurement systems. Okay, stereo measurement we have not done because ours we feel that it is an automated system. So we validated with automated systems. Okay, and stereo always there may be some errors because how you will orient your component, that is a major thing. Okay. I hope those who are working in sheet metal forming, then they know they will put some place so that this grid is normal to your eyepiece, right? So that is very difficult. So whatever we have done with GPA, grid pattern analyzer. You can see here this table. These are the deviations. Yeah, these are the deviations. 8 mm original diameter that we printed. When we measured, it is 8.03. 3 mm minor axis length, we got 2.959. Similarly, with the commercial device also, we put somewhere. Like this, we printed. Okay, even we printed very small grids also, 1 mm, 2 mm grids also we printed and we measured. And it is because you can also use very smaller grids also.
Thank you, sir.
Anyone else?
Okay, thank you.
Now I request Dr. Anita Lakshmi to honor with a gift to Dr. Suresh Garu.